In late 2025, the scientific community was captivated by the discovery of an unusual radio signal originating from the interstellar comet known as 3I-ATLAS, an event that marked a significant milestone in humanity's exploration of objects from beyond our solar system. Detected through advanced radio telescopes and confirmed by multiple international observatories, the signal immediately drew the attention of NASA's Planetary Defense Coordination Office, prompting intensified monitoring and coordination with space agencies and research institutions worldwide. This discovery was not merely another observation of a distant celestial body, but rather a rare opportunity to study material that originated in a completely different star system, offering insights into cosmic processes that occurred billions of years ago and far beyond the reach of our Sun's influence. The signal, though ultimately verified as natural in origin, stood out due to its consistency, clarity, and persistence, distinguishing 3I-ATLAS from all previously observed interstellar visitors. The comet was first identified on July 1, 2025, by the ATLAS Asteroid Terrestrial Impact Last Alert System survey, which was originally designed to detect potentially hazardous near-Earth objects. When astronomers analyzed its trajectory, they quickly realized that this object was no ordinary comet. Unlike typical bodies that orbit the Sun in predictable elliptical paths, 3I-ATLAS followed a sharply hyperbolic trajectory, moving at an extraordinary speed of nearly 100,000 kilometers per hour relative to the Sun. This velocity and orbital shape clearly indicated that the comet was not gravitationally bound to our solar system. Instead, it was a temporary visitor, passing through on a one-time journey before returning to interstellar space. Such behavior is a defining characteristic of objects that originate beyond the Sun's gravitational domain, confirming 3I-ATLAS as an interstellar traveler. Subsequent studies conducted by teams from the University of Hawaii, the European Space Agency (ESA), and other major research institutions classified 3I-ATLAS as only the third interstellar object ever detected by humanity, following the discoveries of Oumuamua in 2017 and 2I Borisov in 2019. Each of these objects had already challenged existing models of planetary formation and interstellar dynamics, but 3I-ATLAS promised to deliver even more detailed scientific data due to its remarkable activity and clear emissions. Researchers theorized that the comet was a rocky and icy fragment ejected from its original planetary system millions, or even billions, of years ago, possibly during a period of intense gravitational instability, when massive planets disrupted smaller bodies and flung them into deep space. Since then, the comet had likely wandered through the vast, cold emptiness between stars, preserving within it a pristine record of its birthplace. What made 3I-ATLAS especially valuable to science was its active nature. Unlike some interstellar objects that appear inert and rocky, this comet exhibited clear signs of sublimation as it approached the Sun's. Sublimation occurs when ice transitions directly into gas under increasing heat, releasing dust and molecules into space, and forming a glowing coma around the nucleus. On October 24, 2025, a major breakthrough occurred when the MICAT radio telescope in South Africa detected a strong and persistent radio signal from a comet at a frequency of approximately 1.6 GHz. This frequency corresponds to the spectral signature of hydroxyl OH molecules, which are produced when water vapor is broken down by solar radiation. The detection of these molecules provided unambiguous evidence that 3I-ATLAS contained water ice and was actively releasing gas, confirming its classification as a true comet rather than a dormant asteroid. This discovery was unprecedented in several ways. While scientists had previously observed gas emissions from comets using optical and infrared instruments, detecting such clear and stable radio emissions from an interstellar object was entirely new. The strength and regularity of the signal allowed astronomers to monitor the comet's activity in real time, tracking how the rate of sublimation changed as it drew closer to the Sun. This capability offered a unique window into the physical and chemical processes occurring within the nucleus, enabling researchers to study how materials formed in distant star systems respond to solar heating. Through continuous observation, scientists were able to estimate the amount of water being released, analyze the distribution of gas in the coma, and model the internal structure of the nucleus with unprecedented precision. Given the extraordinary nature of the signal, rigorous verification procedures were immediately implemented. Multiple observatories around the world attempted to replicate the detection, and extensive tests were conducted to rule out terrestrial interference, satellite transmissions, or other artificial sources. After months of careful analysis, researchers concluded with high confidence that the emission was entirely natural and originated from physical processes within the comet's coma. This confirmation strengthened the scientific significance of the discovery and eliminated speculation about extraterrestrial intelligence or technological activity, allowing the focus to remain on the astrophysical implications of the phenomenon. Although 3I-ATLAS posed no threat to Earth and its trajectory kept it at a safe distance, its unusual characteristics mobilized the international scientific community on an unprecedented scale. Space agencies, universities, and private observatories collaborated to coordinate observation schedules, share data, and develop unified models of the comet's behavior. Optical telescopes tracked its brightness and dust production, infrared instruments measured its thermal properties, and radio arrays monitored molecular emissions. Together, these multi-wavelength observations created a comprehensive picture of an interstellar comet in action, something that had never before been achieved in such detail. One of the most important scientific outcomes of studying 3I-ATLAS lies in its potential to reveal information about planetary formation in other star systems. The composition of comets reflects the conditions present in the protoplanetary disks from which planets emerge. By analyzing the ratios of water, carbon-based compounds, and other volatile substances in 3I-ATLAS, scientists can infer the temperature, density, and chemical environment of its original system. These insights help researchers compare our solar system with others in the galaxy, shedding light on how common Earth-like conditions may be and how frequently water-rich bodies are produced elsewhere. Furthermore, the comet's long journey through interstellar space offers clues about the survival of organic and volatile materials over extreme timescales. Exposed to cosmic radiation, temperature fluctuations, and interstellar particles for millions of years, 3I-ATLAS represents a natural experiment in material preservation. Understanding how its composition has changed or remained stable during this journey may provide valuable information about the resilience of molecules that are considered essential for life. Some scientists have even suggested that such interstellar objects could play a role in transporting organic compounds between star systems, contributing to the cosmic distribution of life's building blocks. As 3I-ATLAS continued its passage through the inner solar system, ongoing monitoring aimed to detect any variations in its radio emissions. Changes in signal strength or frequency could indicate shifts in the composition of released material, structural fractures in the nucleus, or the exposure of new icy layers. Each fluctuation was carefully documented and incorporated into evolving models of cometary behavior. These observations not only improved understanding of this particular object, but also enhanced general theories about comet evolution, activity cycles, and response to solar radiation. Ultimately, 3I-ATLAS will complete its brief visit and depart our solar system, accelerating back into interstellar space and disappearing into the darkness between stars. Unlike planets and long-period comets that return again and again, this visitor will never come back, making every moment of observation invaluable. Its legacy, however, will endure in the vast datasets, refined models, and scientific insights it has provided. The discovery of its radio signal demonstrated the power of modern astronomical technology and international cooperation, highlighting humanity's growing ability to study even the most fleeting and distant phenomena. In many ways, 3I-ATLAS represents a bridge between star systems, a messenger carrying information from a remote corner of the galaxy to our doorstep. Through careful observation and analysis, scientists have transformed this silent traveler into a source of knowledge about cosmic history, planetary formation, and the chemical diversity of the universe. Its journey reminds us that our solar system is not isolated, but part of a dynamic and interconnected galaxy filled with wandering fragments of distant worlds. As technology continues to advance, future interstellar visitors may be studied in even greater detail, but 3I-ATLAS will always be remembered as one of the pioneers that opened this remarkable new chapter in astronomical exploration.